Welcome to this video where we will look at the numerical solutions of PDEs in one spatial dimension, and by the end of this video you will be able to develop code to solve PDEs numerically. So here is the example that we had in the prior video where we went through the 4 steps of how to solve a PDE and transform it into a system of ODEs. Shown here is the Fi, the right-hand side that we derived by replacing the spatial partial derivatives with a finite difference formula, and then also the boundary conditions and initial conditions are here repeated again. So how can one code a solver for PDEs? Well, first of all, you should code a function called BC that applies the boundary conditions. Now, it doesn't have to be named BC, but I just suggest that as a name, BC standing for boundary conditions. Then you should code a function that you can name, for example, my RHS, my right-hand side, that does what? That first applies the boundary conditions and then calculates the right-hand side vector f with the formulas here from the example. And then you code a function, a Runge-Kutta function, some of the my_rk functions, that performs a single step of a Runge-Kutta method. Okay, now here are then the individual steps. The first one is you should define your mesh. That's consistent with step 1 of the solution procedure for PDEs. That means define the number of subintervals m, the length L, the interval size delta x, and the coordinates x of the mesh points. Then allocate the dependent variable, in this case temperature T, as a column vector, and set the initial and boundary conditions for this column vector of the temperature. Then calculate the stable time step delta t and the number of steps, let's call that n step, to reach a desired end time. Once you know the number of steps and steps to perform, you can then calculate or set up a for loop. For loop where the loop variable is little n, going from 1 to n steps. What do? You call the Runge-Kutta function with an argument of your right-hand side function and provide it the current value of time, the current temperature vector, and the step size delta t. Now this formalism is exactly the same that we used for ODEs. So you can actually use the functions that we developed in the prior module for ODEs. Now this function will return and overwrite the current value of the time scalar and the vector of the temperature values. Then you need to apply the boundary conditions to this new time level solution vector t by calling the boundary condition function. And then you can do any plotting or data extraction if that is required. And if you want to look at that, how that is done again, please go back to module 8 and look how we did this for ODEs. It's exactly the same approach. And that's basically the entire code. So let's do an example. Let's code up the handwritten example that we did in the prior video and develop code for it. And I'm almost certain we can develop the code faster than solving these just for 2 steps by hand. So let's start. So I'm just here in MATLAB. I'm in a new folder here, a blank folder with nothing in it yet. And in the recipe that we just looked at, what we have to do first is code a function that sets the boundary conditions. So I'm going to go new function and the name BC, boundary conditions. I'm going to pass in the independent variable that was t and the dependent vector y. And the output is the dependent vector y with the boundary conditions applied. Then never forget to write a comment, what this function is supposed to do. Apply boundary conditions according to the video problem. Okay, list the input variables. Input, we have t, it's the current time. Uppercase y is the vector of dependent variable. And the output is same thing, it's y, vector of dependent variable with boundary conditions applied. Okay, so now we have to set those boundary conditions, and those boundary conditions were that the value at the first point is always equal to 1. Let me just write, set left boundary at x equal to 0. And then I have to set the right boundary at x equal to L. And that boundary condition was that y at the end, I know that that endpoint, if I have m subintervals, is going to be at m plus 1, was equal to the prior value m plus delta x, let me call this dx, times the current time. The current time was t, right? That gets passed in. Now, if we look at this, there's a couple of variables here that we do not know in this function and that do not get passed into the function by the argument list. And that's the variable m here, the number of subintervals that I have, and the spacing delta x. So the instruction said just make them global variables. So I'm going to have a global m and a global dx that I now need to set in my script before I can use this function. Let's save this. Saved up. Okay, so that's my boundary condition function. Next up, I have to make my function for the right-hand side. So new function, my RHS inputs are independent variable, vector of dependent variables, and the output is the vector of right-hand side values f. Okay, comment. This here, calculates the right-hand side for the video problem. Okay. So what's the input? Input, well, I can kind of copy-paste almost from the other function. So let's do that and fix it. So t, y, vector of dependent variables. The output is f, is the vector of right-hand side values. Okay, so good. Now, what do we have to do? Well, first thing was apply boundary conditions. First thing, apply boundary conditions. So how? Well, I just need to call my boundary condition function. Nothing simpler than that, except that my variable is, of course, not uppercase t, but uppercase y. So that updates my boundaries in case they weren't updated yet. Then I'm going to allocate the right-hand side vector for the right size. So f is equal to 0, so I'm going to make this a column vector. So m plus 1 and 1. And even though I need this f only for the interior points to keep the indices straight between the vector y and the vector f, make the right-hand side vector f the same size as y, so meaning include boundary values, even though we don't need them, and they're actually set as 0 right up here. And then we need to calculate f for each interior mesh point. So we have a loop for I equal to m, 1 and m plus 1 being the boundaries. F of I is equal to, well, the formula that we derived, minus x of I squared times backward differences, first order, y of I minus y of I minus 1, right? I'm at grid point I, that's my loop index here, over here. then this entire thing divided by delta x plus x of I plus the current time t, right? That came as an argument up here. Okay, then I can close this loop, and right, that's pretty much it. Let's check here. Yeah, that looks okay. Can save this. That's my right-hand side function. So I coded my boundary condition, I coded my right-hand side function, except that some of these variables here are not known in here, right? I don't yet know what is dx, I don't know what m is, and I actually don't know what x is either. So those have to become global. So I have global dx, m, and the vector of coordinates x. Okay, so everything else here, the y, the t, that comes in as an argument. Okay, so let's code the script to solve this. And let's start like every script with format long, format compact, close all, clear all, CLC for a clean slate. And just as a reminder, I had global variables, so let me just copy them over here. So I need this as global. And from the boundary condition m and dx, I need those as global, but they're included up here. So those are the global variables. I tend to put them at the top of the script to remind me that I have to set those values. So step one was define mesh. Okay, and that comes from whatever we have in the given problem statement. And in here, what was given to us was that delta x was equal to 1, and the length was equal to 4. And with that, we can then calculate the number of subintervals, L divided by dx. Now, these are two double precision numbers that we divide by each other, and because of round-off errors, and m should be an integer number, we'll force the issue here to make it an integer number by rounding the results. It's not going to be a problem with 4 and 1, but in general, if we want to make sure that this is a integer number, we should use the round function. And then we can calculate the grid. X was the linspace. Oops. What happened here? Okay, it was the linspace from 0 to L using m plus 1 points transposed to make it a column vector that defines the mesh locations x sub I. Okay, then allocate solution vector and set initial and boundary conditions. Okay, so y has to have the same size as the x vector. So y, let's allocate this as a column vector, m plus 1 entries as well, right? Because we have m plus 1 points. And the initial condition for this was all y values were equal to 1. And then I have to apply the boundary conditions that I just do by y is equal to bc of, well, I have to define my initial time. Well, my initial time is 0. So with the time being defined, I can pass into the boundary condition function t and y, and thereby set the boundary conditions. Okay, next set the time step and number of steps. I have to set a delta t. The delta t that was given in the problem, delta t was 0.1, and then I should set an end time. The end time wasn't really given, but when we did this by hand, we went to an end time of 0.2. Let's go at least twice as far. Let's go to 0.4. With the end time and delta t, I can calculate how many steps I need. That would be end time divided by dt. But I want this to be an integer number as well, so let me make sure that round-off errors don't cause me any issues. Let me round this result as well to find the number of steps. Okay, so I have everything set up. I can now solve the PDE. I do a loop for n equal 1 to n steps, right? That's the number of steps that I need. I will call my RK method of choice. So Ty is equal to my RK, let's do RK1, right? That's what the problem stated we should use. My RK1, I have to pass in the function that calculates my right-hand side, which is my RHS. Oops, where did I write this? There. My RHS. That was it. That's the name. Then I need as arguments. Let me first copy over an RK1 method from the module. See here, let me go into the right directory. There we go, now I'm in the right directory. I need an RK1 method. So let's copy over an RK1 method. That's basically the same thing that we did for the ODEs, right? So there we go, I've got my RK1 method. Why did I want to copy this over? Because I wanted to look at what the arguments are. Okay, so I need my current independent and dependent value vector. Okay, so current independent vector is T, current dependent vector is Y, and then I need the step size dt. There we go. So that updates using RK1, and then we have to apply the boundary conditions. So apply boundary conditions. Y is equal to BC of T and Y. Okay, and that's it. That would solve the system. Let me save this here, example. Save it like this. And let's see what happens. Let me make this a little bit larger here and the variables. And let me put a breakpoint right here and run this code. And if I make this even larger, we can actually look at what the x values are and the y values. The x values 0, 1, 2, 3, 4, right? They go all the way through the domain. And the initial values for y were all 1. That's what consistent what we had handwritten as well. So let me click step. I do one solution, and let me directly apply the boundary condition. Let me type y here to see what the results are. 1, 1.1, 1.2, 1.3, 1.4. That should be what we have found as well when we did this by hand. So let me hit more continue one more time and do a step and see what the solution then is. 1.0, 1.2, 1.37, 1.52. Well, but I haven't applied the boundary condition yet. So let me do another step to apply the boundary condition. And then I get the solution 1, 1.2, 1.37, 1.52, and 1.72. And that should be the result that we obtained when we did this by hand. And I'm just cross-checking that's exactly what it is. So that's how you would solve this. And now we can, of course, do a third step in just a fraction of a second here. That would be the y values after the third step. We can do continue, continue. That would be the y values here after the fourth step. So what else can we do in here? Well, we can plot the results, right? We can plot on the x-axis the vector x, and on the vertical axis the vector y, and can make the line width a little bit larger. I can set the font size to larger, otherwise it'd be hard to read. I set a label for the x, that would be x, and a y label, that would be uppercase y. Okay, and what else? Well, I should kind of write out what the current time is, right? So let's write into the let's write into the title with sprintf. Print a string that is t is equal to placeholder for the number, and the value that I want to write is the time value t. Okay, and then I'm just going to do draw now to force the issue and draw this graph right away. So let's put a breakpoint right here at the end. Let's run the code. Okay, so that is the solution after one time step. If I hit continue and bring the window back up front, that would be the solution after two time steps. Continue, bring the solution back up front. Solution after three time steps. Well, let me just hit step to print actually the title. There we go. So now t is equal to 0.3. And then if I hit one more time, continue, I'll just run it all the way through. Let's run it just one time all the way through. Right, you see that this would be the solution after 0.4 time units. So the key really to coding PDEs and solving PDEs lies in calculating your boundary condition function, calculating the function to calculate the interior values of the right-hand side vector f, and then just using one of the RK methods that we had in the module on ordinary differential equations and calling that successively in a time loop here where we advance the time from the start time to the requested end time. Okay, thank you for watching.